They're clapping because it's the last one.
They're going to summarize everything we had in the winter school. And more in his last lecture.
Okay, so this is difficult to do. And to be honest, it doesn't really constitute a summary because we've covered too many things and my brain has a finite size. But I do want to talk about the nature of the field that we have been discussing at this school and where it may be headed and where you are headed, since I presume you're going to do research in exoplanets. Of course, more immediately you may be headed home or back to school, but perhaps you are also headed off into the wonderful world of exoplanets. A few thoughts about where we came from. This is a personal comment. I went to a conference after completing my PhD at Cornell. The conference was at Newcastle upon Tyne in 1976. And it was actually a fairly famous conference. Among other things, it was the conference where the discovery of aluminum-26 was first announced. Hannes Alfvén was there, Al Cameron, all sorts of other people who were prominent in the field at that time. And it's interesting to think back about that meeting because in that meeting there was a discussion without data, essentially. That didn't stop people. So there were all sorts of unconstrained speculations, and there was actually, despite the lack of data, quite a bit of confidence about what people thought was going on, and a lot of it was wrong. And indeed, in many areas of science, you have a situation like this graph here, which of course is on a log scale. So the vertical axis is intended to represent the self-confidence of the scientists as they talk to each other. How much do they think they actually know? And the horizontal axis is intended to represent data, that is real understanding, real knowledge. And it is actually true in many areas of science, not just in this one, that often one has a curve like this, which may in fact oscillate, in which people think they understand something, and then as more data are collected, they realize they didn't really understand it at all. I've presented our situation optimistically. You can decide for yourself whether this is true, and you can decide for yourself whether we're going to do that or whether it's something else. But the point is that as we collect data, many of our previous ideas turn out to be wrong or to require a great deal of modification.
What was the lowest point? Is there any remarkable events that make you think? I mean, the lowest point in between. What was the remarkable event or whatever that makes you think that we don't know anything?
So, yes. I mean, the discovery of giant planets close in is a good example of something that really greatly changed our picture. When I went to graduate school at Cornell, I can remember being in a class where, by atomic orders it happened, where a very nice story was told about why you have the terrestrial planets where they are, why you have the giant planets where they are, why you have the ice giants where they are. And very little of that survives on the basis of the data that we have now. Some of it may work still for our solar system, but the point is that they're not general statements. It's worthwhile reflecting on the role of theory, in particular for the field we're in, which is one where we are receiving an immense amount of data. And so it's very data-driven. That's not true of all the areas in physics. But this area is very heavily data-driven. And as a consequence, the role of theory, at least at present, in the exoplanet game is, to a significant extent, a response to observation. There's nothing bad about that, but it's a statement of fact. That is, somebody presents you with some new data about where planets are and what they are, what kinds of planets, and so on and so forth. And you scratch your head and you say, well, maybe that's because of such and so. And that's okay, but that's the nature of the field that we're in, that we are often doing theory in response to observation rather than ahead of observation, and we're looking for patterns. So we look at the data and we try to discern something that fits some idea we have about how things work. Now, for many people, the strength of theory lies in the ability to make predictions and to falsify those predictions. This is the philosophical point of view of Karl Popper. Not everyone subscribes to it, but it has some merit. Clearly, we have more confidence in what we're doing if you can come up with a theory which can then be tested by subsequent observation and turns out to be right. A classic example of that would be Einstein's work in general relativity. At the time that he completed that work in 1915, he did, of course, do a calculation for the anomalous precession of the orbit of Mercury, but in a sense that was also a prediction, because what he was basically saying when he did that calculation is that you did not need to have a planet interior to Mercury. At that time, one of the alternative explanations was to have a planet called Vulcan, which was closer to the sun, and it doesn't exist. So in that sense, it was a prediction, and of course the deflection of light by the sun, confirmed in 1919, likewise. In planetary science, an example of a prediction that turned out to be correct would be the work of Goldreich and Tremaine on some of the structure in Saturn's rings. It was a prediction, and it turned out to be verified by the Voyager spacecraft. The question we have to confront is this: to what extent can we hope to do things like that, or are we instead in a situation where the science that we're concerned with is intrinsically messy? My own view on this is that it depends on the kind of problem that you're attempting to solve. Sometimes in dynamics, one has a evident beauty in the arguments, the kind of thing that Joram Lifwick talked about, Scott Tremaine talked about, and Rame has talked about. Many of those problems have this inner beauty, Hamiltonian dynamics and so forth, where you might hope to have some aspect of the problem isolated and clean enough that you can make predictions and go off and test them. In many other areas of exoplanet study, I would suspect that that's not the case. For example, in the chemistry of atmospheres. It's just simply too complicated. It becomes more and more like biology, which, as one eminent biologist once said to me, is the science of exceptions. That is, it resists the approach, the inductive approach that physicists like to use when they do their science. It resists generalization, and to some extent that may be the situation that we're in with exoplanets. We certainly want to be motivated by observation, and you would hope that theorists and people right here among you, that you would have the imagination to come up with something that motivates observation. So you have some idea, perhaps to some extent motivated by data, but looking beyond the current data, and then you go to an observationalist, to an observer, and you say to that person, hey, I have this idea, why don't you go away and measure such and so? And imagination often comes in circumstances where you have imperfect knowledge. This is an interesting point. And so it's actually a good thing to be a little bit ignorant. If you know everything or you think you know everything, you may actually stifle your imagination. It has to also be conceded that in the history of exoplanets, theorists have sometimes been an impediment. To some extent, that was true for Kepler. I can remember in the 1990s attending a workshop at NASA Ames, Baruchi up in front of the room. It was a small room, smaller room than this, and I don't remember the specific circumstances, but it was in the very early days of thinking about a mission like Kepler, and Bill was describing what could be done, and there was evident skepticism in the room, which came from a prejudice about where planets would be and how common they would be. So in that case, theorists were an impediment. But let's be more optimistic and hope that you can help by coming up with ideas that would motivate observation. Now, a lot of what I've said so far has to do with only part of what we do when we study exoplanets, and that is understanding origin. Where do planets come from? What determines the variety that we see? But of course, there's another aspect to exoplanet studies, and you could call it comparative planetology. For indeed, one of the things that many of us like to do is to take some aspect of what we think we understand about planets, for example, atmospheric circulation, and try to generalize it, come up with a general framework. What happens to the atmospheric circulation if I change the day to night temperature or equator to pole temperature, or I change the rotation rate, or I change the relative amount of heating from the outside to heat from the inside? These are actually quite fundamental questions. And they have not been solved by looking at the planets in our solar system. We actually do not understand at the present moment why it is that Uranus and Neptune do what they do, why Jupiter does what it does, how deep the circulation is. Some of these things are very hard to solve with studies of exoplanets, but in many cases you can get some insight into the dynamical regimes, and we saw that in some of the presentation from Adam Shulman. So other examples would be with magnetic fields, with atmospheric composition and so forth. So there one is confronting the fact that you have a very wide range of possibilities, and you're trying to extract from that some generalities about how things behave as you change parameters. And the whole idea of scaling, how things scale as I change the mass and the radius, rotation rate, whatever, emerges from that. And exoplanets play an important role both in the sense of understanding the exoplanets, but in the sense of understanding the basic phenomenology, how atmospheric dynamics works and so forth. Of course, for many of us, what we want to do in the end is tell a story. That is a essential part of science, storytelling. Essential for the kind of science that we're doing, because it's different from laboratory experiments. You can't go away to the lab and build your own planet. So you have to study planets, and that's what makes this area of science, and indeed most of astrophysics more generally, and planetary science more generally, that's what makes it more like biology. You're studying things the way that they are. You're studying the natural world. You're not doing experimental physics on a bench or in a laboratory. And so storytelling is a very important part of it, and you know, everybody has this, not everybody, but many people have this notion that this eventually leads to some sort of grand synthesis. So developing just a little bit on this somewhat philosophical introduction, it seems to me that there are two kinds, at least, of theory, the way that you approach theory. And here I'm talking about low entropy and high entropy in the sense of Shannon, in the sense of communication theory, information theory. And what I would call a low entropy theory is where you propose a theory, you compare it with data, and then you reject or confirm. Of course, you never really confirm a theory, but you show to your own satisfaction and other people's satisfaction that it satisfies the data. And then you say, okay, that's wonderful, let's move on to the next thing. A more common thing is high entropy theory, where you propose a theory, you compare with data, and you say, oh, I have to change my theory. So, but you don't give up on it. You change it. And then you compare with data, and you modify, compare with data, modify, and you end up in a whirlpool. And along the way, of course, you're creating a very fluffy theory. Fluffy because it doesn't have sharp boundaries to it. You're perfectly happy to add on this and add on that and have this exception and that exception, and so it becomes increasingly fluffy and high entropy. And actually, I would say that we are in danger in many aspects of exoplanets of being in that situation, of having fluffy theories. And that is, of course, a problem. So Bertrand Russell, a famous philosopher and mathematician, said that everything is vague to a degree you do not realize till you have tried to make it precise. There is another problem in our field which has more to do with modeling than theory per se, and that's what I call low imagination. This is actually very, very common in the exoplanet community. A lot of papers, if you took a census of the papers published in AppJ, theoretical papers, modeling papers in exoplanets, they have this problem, in my opinion, which is you take some existing description of how a planet works and you just tune parameters without thinking about the fundamentals. In other words, you assume that the fundamentals were put in place when people thought about how the Earth worked. And in my opinion, that's often not true. You actually have to go back to the fundamentals because the richness of exoplanets, possibilities, is so great that it's a mistake to start with thinking about the Earth as the basis for talking about exoplanets. So I think this is a very common problem. Of course, related to this is the problem of using our solar system as a guide. This is now less common, and that's good, but people still tend to use the solar system as a guide, especially when they're talking about the so-called Earth-like planets. The problem, of course, with low imagination theory is that it's more likely to be funded or supported, so there's an unfortunate encouragement. And this reminds me a little bit of something that Einstein said, which is his definition of insanity, doing the same thing over and over again and expecting different results. Now, I'm reinterpreting what he's saying here, but what I'm using that statement for in this regard is the notion that you can understand exoplanets by taking something that you've already understood without thinking about the assumptions that went into that understanding, and then just turning the handle and expecting to get a full understanding of what's going on. Okay, so what I'm going to do for the main part of this, and I should say that I don't expect to fill the full 90 minutes. I'm hoping towards the end of this to lead this into a general discussion that you should all participate in. So I don't actually have a large number of slides. But what I do want to do is to go back to this slide that I showed in my introduction, which is actually about observations, and then talk about each of these items in turn and what is going to happen next, what is happening already, the role of theory, and so forth. So the first one, of course, is just the question of existence. This is, of course, the most spectacular thing that has happened in the science of exoplanets, the remarkable richness of exoplanets. And what we have seen emerging in this field, and it showed up in this school, is the fact that there are observational biases, and therefore we don't yet have a complete picture. So yes, we know that planets are common. We have these ideas about the percentage of various planets as a function of semi-major axis, mass, metallicity of the star, and so forth. But it's an incomplete picture, and so that is the challenge for the future, and it is also, if you want to take it on, the challenge for prediction. Can you predict what you expect to see and use that as a basis for deciding whether to keep the theory you have or throw it away? The relation to elemental abundances is important. We saw that right now in Giovanna's talk, but it came up, of course, earlier when Dave Charbonneau talked about the data and other people talked about the data, the role of metallicity. To me, one of the interesting issues here, simply because we don't have much data yet, is the number of free floaters. You should recall that when Rehm was talking about formation of planets, in the way he set it up, it is quite likely to have ejection of planets from the planetary system, and in some theories the number of planets that are ejected are of the same order, certainly same order of magnitude, but maybe even similar in actual number to the planets that we can see. They are hard to see. Many of these planets would be very hard indeed to see. I got involved in thinking about this a decade or so ago, talking to Dimitar Sasolov about the different ways in which you might see them. At the moment, it would seem as though our only hope is microlensing. But this is an important test of our understanding. Is it the case that free floaters are common, or is it instead the case that they're relatively rare? This would seem to be an important test of many of our ideas. But the other thing that we have to do, keeping in mind that all possible niches are occupied, that's the history of astronomy, of course. I hope you all know this. Basically, anything that is permitted by the laws of physics, one usually finds something. Okay? So we have to look in unexpected locations as well. Planets around white dwarfs are not unexpected, they're just hard to see. But of course the first exoplanets discovered were around a neutron star. That was a somewhat unexpected thing. It's valuable to think through the possible unexpected locations for planets and look for them. Look for them in the unexpected places. We talked, of course, about the importance of characterizing the central star, and that would seem to be something that will continue to be important. Asteroseismology, also the astrometry kind of information that will come, that is coming right now from Gaia, will come perhaps from Plato. That's a very important observational constraint that will lead to more precise determination of radii and masses for the planets. And then, of course, the orbital parameters. When you find the planets, you characterize where they are, semi-major axis, eccentricity, and inclination. And this is a very important constraint on our ideas of the dynamics. The role of scattering, the role of tides, the role of secular evolution, which Yoram told us about, Lidov Kozai, whatever. All of these aspects of orbital behavior are related to the history of the system, and by measuring those things, understanding them, we can develop a better understanding of how the system was put together. I've added to that something that is hard, but may eventually be possible, and that is the spin of the planets, length of day of the planets, and their obliquities. One way that you could, in principle, do this is by magnetic fields, and I think that will probably pay off for giant planets at least. Maybe hard for terrestrial planets. Of course, obliquities, we don't really understand that in our own solar system. So that's a challenge even for our own solar system. But in a utopian vision of where exoplanets goes, if you could get that information, the distribution of spin periods and obliquities, that would be a fascinating data set. I'm not saying it would be easy to interpret. It doesn't lead immediately to some profound understanding, but it would be part of a deeper understanding of how these planets formed. What about the architecture? Now this is the one that is closest to the grand synthesis. I very much liked what Ruth told us. She presented us with a challenge, a testable framework. She said to us, these are the parameters that matter, and that we can understand systems on the basis of where they lie in this diagram, the extent to which you have something that looks like our solar system, or something that has super-Earths, something that has giant planets, or something right at the top of her diagram, she had things all messed up. When the surface density got high enough, things got scrambled. So this is a testable framework. It is, of course, just a two-dimensional representation of something that has other dimensions. And so one of the challenges for the field is to decide whether this is the right way to think about it. Doesn't have to be. Radius, of course, to some extent, coupled with surface density, is a proxy for the angular momentum budget. Surface density in part, but not entirely, a proxy for metallicity. But this is, I think, a very interesting way to think about the problem of architecture, and whether or not Ruth is correct in detail, I have to congratulate her on taking on the challenge of presenting a framework in which to think about these things. What, aside from metallicity, determines the disk condensable mass? To what extent is the kind of approach that people still use, and actually Ruth used in her first lecture, even a good way to think about the problem? She started with the minimum mass solar nebula, and we went back to it on a couple of occasions. There are many problems with thinking about the problem in the context of the minimum mass solar nebula. One of the problems is this idea that if I specify a total surface density, that also tells me how much surface density of condensables I have. That is the heavy element component relative to the total the same at each place in the disk? It doesn't have to be, because once I start forming solid bodies, they can move at a different rate than the gas. And so in principle, you can have a dust to gas ratio that varies with location in the disk, even though the entire thing has some relative amount of solids and gas that is given by the metallicity. The particular scaling that we have used in our solar system that is not coming from any theoretical idea that the surface density goes like out of the -1 or out of the -3/2. Where does that come from? There's some very basic problems there that we don't yet know how to solve. To what extent is the starting condition in terms of what you have in this diagram, where you lie in this diagram, is that a random variable? Or is there something that we haven't yet discerned about the way that material is delivered during Jeans collapse, which is actually more complicated than Jeans collapse because stars are popping off and you've got a very complicated environment, we think, when stars form. To what extent is there some coherent pattern to that? This is something I will come back to later in some general comments at the end, but it ties, of course, to the basic idea that we need to understand star formation and disk formation somewhat better. But this is, of course, where the grand synthesis lies, and it's guided to some extent by finding patterns, but also by grand ideas. I mean, yes, of course, you can do theory by looking for a pattern and then saying, where does that pattern come from? But you can also think about this on a desert island and just ask yourself, what are the main ideas that dictate the form that a planetary system takes? And in doing so, of course, you have to be wary about where the missing gaps are in the theory. This, of course, is a very famous Sidney Harris cartoon where one has some theory. In the case of planet formation, the miracle is often said to be planetesimals, although I thought Urim did a pretty good story summary of where we stand at the moment. It looks as though you can do it, but for a long time people thought that the planetesimal formation was the biggest problem. It's not clear actually whether that's true. You might argue that Uranus and Neptune are the biggest problem. At the dinner after Ruth's talk about her picture of the solar system, that was actually the thing that concerned her most. It's not clear that we really understand how Uranus and Neptune formed. It's a timescale problem, getting the right amount of gas. It's all a little bit puzzling at the moment. And so in some sense, when people say this happened and then that happened and then that happened and so forth, the story has these elements that look a little bit like miracles about getting Uranus and Neptune to come out right. So you have to be thinking about the extent to which your theory may look wonderful at two places but has a bridge in between that is very wobbly. We heard quite a bit about mass and radius. Dave Charbonneau made a big issue of this because of the story which he has been largely responsible for, which is that a very small set, but nonetheless well-characterized set of SuperEarths actually lie on the compositional radius-mass line for Earth or near-Earth composition. That's an interesting result. But of course, there are lots of objects that don't. My summary statement here would be that in respect of the condensed part, the materials that are degenerate matter as distinct from gas, this is a well understood problem. By that I mean theory has this well in hand. It's not as if we have some major mystery about how materials behave at high pressure. We don't. There's no evidence that we have some difficulty there. So the basic principles here are understood. That is, the equation of state is well enough known. Now, of course, if you get to really, really high accuracy, like 0.5% or 1% of the radius, which is a couple of percent in the pressure density behavior, then you start to have doubts, although there the most likely thing you do is you trade it off against composition, change the amount of iron or whatever. So the big issue here, as I see it, is the puppy atmospheres. Because we see in the TTV bodies that these are fairly common, and in some cases surprising. In what sense are they surprising? They're surprising because they exist in an environment where you would worry about whether that atmosphere can be retained for billions of years. And so there is a puzzle there, and there's also a question of what the systematics are telling us. In other words, you've got a radius mass diagram, you've got a bunch of points that sit above the condensed radius mass relationship telling you you've got these atmospheres. But why is it 1% rather than 0.5% or 2% by mass in the form of the atmosphere? How does that change with time? How does that change with location? Is there a process of replenishing the atmosphere? There are a lot of interesting issues there with escape and outgassing and time variation. And so this is a good point at which to offer the comment that it would be of great value, though hard, to be able to take our exoplanetary observations and bin them according to age. This would be spectacular. Imagine if you had a data set where you had the exoplanets that are less than 1 billion years old, 1 to 2 billion, 2 to 4 billion, 4 to 8 billion, or something like that. That would be spectacular because these are the planets, the puffy ones, that are going to change, and to some extent perhaps the hot Jupiters as well, although that depends on the mechanism that you want to use for inflating them. So the element of time is one of the directions for the future. Can we develop a data set that is so rich that we can get time? How do you get time? You get time by knowing the central star well enough. This is not easy, but the astroseismological data together with our well-developed understanding of the evolution of stars in principle can give you time to 10% accuracy. Maybe not for all stars, but in many instances you can do that to 10% accuracy, and then you start to have a data set where you can divide things up according to their age. And I think this is one of the most exciting things in terms of the radius mass diagram. I come now to the question of atmospheres and surface composition. In my opinion, this is the greatest prospect in exoplanet science. When I say that, I don't mean to play down the importance of the kind of data we're getting already. And I also don't mean to imply that understanding the atmosphere is going to be easy. And it's possible that we will have trouble, because it's possible that many of these planets have clouds, and that makes it harder to understand the richness of atmospheres. But I would argue that when it comes to understanding the true nature of these planets, the atmosphere, or surface if you're so fortunate to be able to get information on that, is crucial. And this relates to the things that Giovanna was talking about. It is, of course, an optimistic view, because this may be a mess. There may be such a richness of alternatives that it will be hard to disentangle the information and tell a story. But in principle, there is a story there. There is a story there for why CO2 exists in the atmosphere of Venus, for why it is at a lower abundance for the Earth, for why Mars has rather little CO2. There is a story about the enrichment relative to hydrogen and helium in the atmospheres of the giant planets. Why is it that methane and other gases are 3 times enriched in the atmosphere of Jupiter rather than being solar? There's a story there about how the planets formed. And in the case of terrestrial planets, a story about how the inside reacts to the outside. In the case of the Earth, we still don't have some aspects of that story fully understood. But water, for example, which we all believe to be important, is part of that story. For example, the water molecules in your body, most of them were probably 1,000 kilometers beneath the surface of the Earth 2 or 3 billion years ago. You are part of the water cycle of the Earth. As water is taken out of the Earth, put into the hydrosphere and atmosphere, and then put back in. And the cycle time is very long. The information there is in the amount of water, in the D to H ratio. As Giovanna correctly said, it would be very hard to do oxygen isotopes, but in principle it's also there in the oxygen isotopes. But D2H you can do. D2H is special because it varies by such a large amount, and the amount is an important thing. It tells you something about the environment. I would like to think, and here's a challenge for you, that by looking at the atmosphere you can decide whether the planet has a surface even though you can't see that surface. Because that surface is a place where you can have exchange of material, and the thermodynamic conditions at that location affects what you see high up. The atmosphere should never be thought of as disconnected from what's below. That's not true of any planet in our solar system, and so it won't be true for planets elsewhere also. Now, I'm saying these things in part as an optimistic challenge rather than based on a full understanding of exactly how you're going to do this. But it is entirely likely that this is the biggest thing that you will see happening in exoplanets in the next decade. That when you go to an exoplanet conference a decade from now, this is the thing that you will see that causes the biggest change in our understanding of planets. The fact that people have more data on atmospheres and a growing appreciation of what atmospheres can tell you about the history of these planets. An appreciation that follows the same path that we've had for the Earth, in which the nature of our atmosphere tells us something about our history. But it is hard, and so I'm expressing optimism rather than certainty. There is, of course, something else that you would like to do for exoplanets that is even harder, and that is figure out how much heat is coming from below. Now, in our own solar system, we can do this for Jupiter, Saturn, Uranus in principle, although that's an example of the difficulty, because in the case of Uranus it's only an upper bound. But we can do it for Jupiter, Saturn, and Neptune, and oh, by the way, we can also do it for Io and Enceladus, but that's because of tidal heating. What that tells you is that the best hope of getting the internal heat budget, which is telling you something about the evolution of the planet, perhaps about how it formed, lies with the more massive planets, simply because their intrinsic luminosity is greater, and also with planets that are more distant, because you can't even do it for a hot Jupiter. The amount of energy might be 1 part in 1,000. It's important for the planet, but it's small compared to the insolation. In the case of Earth itself, it's actually hard. The amount of energy coming out of the Earth's interior is 5,000 times smaller than the amount of energy absorbed as sunlight. And that means if you put a satellite in Earth orbit and it looks down at the Earth, it can't actually, with sufficient precision, give you a number for the amount of heat coming out of the inside of the Earth. It has never been done to high accuracy from Earth orbit. It is done the old-fashioned way by sticking probes in the ground and measuring the temperature gradient and knowing the thermal conductivity. That's the way it's done. And you're not going to do that with exoplanets. But you may, of course, get indirect indications of the energy budget of a planet through magnetic fields, because the way in which a planet has a large magnetic field is through the dynamo process, and the dynamo process depends on convection at depth and therefore has implications for the amount of heat. And so by having enough information about which planets have magnetic fields and which don't, you might be able to build a story about the energy budget. And of course you can also look at young systems, because in young systems, Jupiter itself, if you look at a system where a Jupiter-like planet has just formed, it will probably have a luminosity about 10 to the minus 4 that of the Sun, which is detectable in the infrared. It will have an effective temperature of 500 or even 1,000 Kelvin, depending on radius, be popped up a bit at that point. So those are directly detectable. So direct detection for young objects is an important part of understanding that issue. And of course, magnetic fields can tell us, as I've already mentioned, about the rotation state. Magnetic field of Jupiter tells us the spin rate of Jupiter. We don't look at the clouds, we look at the magnetic field. But you look at the clouds to determine differential rotation. You don't look at the clouds to determine the rotation of the planet. And it can tell you, as I said, about the nature of the interior and maybe atmospheric evolution, because there are circumstances in which the rate at which gas escapes depends on the extent to which it gets ionized, and once it's ionized, the outflow of the gas depends on the magnetic field. That's true for the Earth, by the way. The escape rate of helium from the Earth's atmosphere is affected by the magnetic field. And then, of course, there's the whole business of smaller bodies and moons. And when you think about how the science has evolved in our solar system, an enormous amount has been learned by looking at small bodies, by looking at comets, by looking at the Kuiper Belt. You saw that in some of the things that Rem talked about, and others have talked about. This is an immensely valuable probe of the conditions in which the planetary system formed. And that can go all the way to dust. So if you see the zodiacal dust of an exoplanet system, that's telling you something about the conditions in that body. If you can detect something about the presence of small bodies in that system through the fact that they occasionally collide with the star, or in the early history of the system, they're colliding with the planets, that would be another way of getting information. And the formation of moons in our solar system have told us important things about how planets form. We don't fully understand how moons formed in our solar system, but the stories that we have developed are giving us information about the conditions during the formation of the planets. The Galilean satellite system, the Saturnian system, we think, are the outcome of a disk that formed around those planets. If you can find comparable systems elsewhere, it will tell you something about the conditions in which those systems formed. There will be plenty of time for discussion, and I'm almost at the end, but I have a few additional general thoughts, which to some extent I've already introduced, but I want to, in a summary form, say something about them. When I think about the grand synthesis, it seems to me that understanding disks is an extremely important part of it. It shows up, of course, in Ruth's way of characterizing the diversity of systems, but more generally, we can see that the way that a disk forms, the way it evolves, is crucial to understanding the outcome for the planetary system. And this issue of how the angular momentum is redistributed, the viscosity as we call it, well, it's not really a viscosity, and it doesn't necessarily have to show up in the dynamical equations the way viscosity does for conventional fluids. But anyway, that mechanism for redistributing angular momentum is clearly a very important part of understanding the conditions under which exoplanets form. And in the history of this subject, what happened, I know because at one time I tried to contribute to this field, but not very successfully. What happened is that initially people were thinking about things like convection, and then they realized that convection doesn't work, or that Indeed, in some cases, convection doesn't even happen. And then along came MRI, magnetorotational instabilities, as one possible way. There may be other fluid dynamical instabilities. And of course, you can also have something that looks like viscosity during the accretion phase when you're delivering material with a different angular momentum budget than the disk to which it arrives. But one has the suspicion that MRI is not a sufficient description because it doesn't work everywhere. This is an instance, I think, of something I said earlier on, right early on in this summary, of a theoretical construct where people modify it or shrug their shoulders and hope that somehow everything will work out. But the fact is, it's not a particularly clean explanation everywhere in the disk. There are places where it almost certainly doesn't work. And as a consequence, it would seem likely to me that we're missing something. Is this a case where people modify the theory and keep modifying it, or is this a case where we really have to go off in some other direction? But the observations are crucial here, and so I want to emphasize something that didn't really get a great deal of attention at this school, which is the observations of disks. Yes, it came up on occasion, but just because of the nature of the school, there wasn't a great deal of attention paid to that relative to the attention paid to the things that emerge, we think, from disks. You may remember we had this discussion of about whether the disk story is even the right framework. I'm assuming in this point that in fact it is the right framework for lack of something better. But assuming it is the right framework, we are still stuck with this disconcerting situation that we don't really know how disks work. And yes, you can do theory, but it would seem likely that a very important part of what we need to do is to get more observations, of what's actually happening in disks. Yes, there are people doing this. The formation of giant planets in disks. This is going to be a very important part of the future of this field, at least for those people who want to make a story about how planets form by looking at exoplanets. In summary, what I'm saying on this point is you're not going to understand how exoplanets form by looking at exoplanets. You're going to understand how exoplanets form by looking at the combination of exoplanets and by looking at disks, by looking at very young systems. I say disks, what I really mean is the first few million years as a star formed. And of course part of that is when detectable bodies emerge. This would be in the infrared mostly. And of course this is relevant to understanding the rapidity with which you make big objects versus the stories where you may have to wait longer because you have the isolated embryos which then have to develop crossing orbits and you have giant impacts and so forth. So it's telling you about timescales, telling you about process. My second point relates to my enthusiasm about atmospheres, but also to a philosophical point about the structure of the science. In astronomy, the history of the subject is an enthusiasm about categorization. I mean, the whole business of talking about spectral type, organizing bodies into categories, families of bodies, as distinct from the individuality of the bodies. And of course, you have such a hell of a lot of data and a number of stars that this is a natural thing for astronomers to do. And it works to the extent that stars are simple, which indeed they are. Stars are simple compared to planets. My guess would be that this is not going to work for exoplanets. that it's probably the wrong approach to imagine that you're going to follow the same path as astronomers did in the development of their subject, which is why I am hostile to those people who like to imagine that there's an HR diagram for planets. I don't think that's a meaningful goal. And the reason, of course, is that planets are complicated. They're complicated in respect of their environment, in respect of their chemical makeup. The variation among stars is small by comparison. And this leads to a way of thinking about the science that is more like what actually happens in planetary science. Because the most important thing, in my opinion, that we learned in the last 50 years from planetary exploration is that generalities don't work. Planets are individuals, and that's a richness, a diversity that is intrinsic to the nature of being a planet. It is astonishing, in fact, the extent to which our aspiration for generalities has failed us. Occasionally you can find generalities in particular issues, such as some aspects of dynamics. But when it comes to characterizing the planets themselves and looking at the diversity of composition and atmospheres and history and so forth, generalities don't work. The striking difference between Earth and Venus is just one example. When people talk about the surprises that emerged from planetary exploration in our solar system, in essence what they were talking about is the failure of this notion that some general picture would emerge. The planets are individuals. Now that becomes a challenge because, of course, if you've got thousands of planets, are you going to give them all names and talk about Joe and Bill and Jane? And I guess not, but it does mean that you have to imagine the best way of organizing your understanding in this multidimensional space. In the end, there will be some categorization, and we do it all the time. But I predict that a lot of that categorization will break down. This is one of the reasons why I'm very uneasy when people use the word SuperEarth, because to me the things that people are calling SuperEarths are nothing like the Earth in most cases. And so by using a name like that, they're already prejudicing their understanding of the body and failing to acknowledge the diversity. So I think our solar system tells us, and the exoplanet observations so far tell us, that diversity is the name of the game. In a sense, that means the planets really are individuals, and we have to live with that and think about the best way of organizing that. So I've left lots of time for discussion, but I'm going at this point with my last slide back to my first slide, the one I showed at the beginning of my introductory talk, to make just a couple of final comments. I think this has been a very successful school. It has been very different from a conference, and that's a good thing. It has clearly been stimulating to many of you, and it would seem that many of you have benefited a great deal from it, and that's delightful. In setting up the school, it was a joint endeavor in deciding who the speakers would be and so forth between me and Raim Sari. But I wanted to take this opportunity right now to acknowledge the work that Raim did, which was considerably more than me, and to thank him on your behalf for all of the effort he put into this. And it's not just the science. The business of crawling around in caves, which bruised my elbows and knees, was a memorable experience. And that's distinctive, okay? I mean, the schools that are held here have certain kinds of things like going to the old city and so forth that are fairly standard, but Rain made this experience distinctive, and so I think that is a major part of what makes this such a memorable school. So I want to thank Rain for that. Thank you.
To thank Dave for the wonderful job he has done. You shouldn't understate how much work he has done to organize all this conference. You also get this little present.
Thank you.
You deserve much more, but...
And what I'm hoping for now in 30 minutes or thereabouts is a bit of discussion. You don't have to just talk about the points I raised, but anything.
I think, Dave, you have not missed a single lecture in this school, is that?
That's true, yeah. You've missed some.
I've missed some, yes. Is there anyone else here that has not missed a single lecture? Wow. Wow. Very good. Discussion. I'll run into the microphones.
Just to be the devil's advocate and talk about a little bit of uniformity, I would suggest a little bit of discussion on where the number distribution, where the Easton distribution peaks. We talk about this in vague sense, temperatures being higher or lower, but I think, okay, I know I pushed 2 peaks in the gap, but in the iron pore distribution, there's clearly a number peak. And where this happens is a function of period, I think is an interesting pattern that repeats over and over and over again. I'm not sure exactly how it changes with the mass, say the mass of the star, but there's probably a small pattern there. So uniformity can teach us some.
Yes.
I'd like to collaborate with people on exploring this and where these peaks are and how that relates to, I don't know that much about formation, so I need some collaborators with that.
Yeah.
Okay, we have an invitation. Any other topics for discussion?
This is a little off the topics we've been discussing, but since Dave ranged so widely in his discussion, one of the things we haven't brought up is that the relation between exoplanet science and the public. Obviously, this is a subject with tremendous appeal for broader audiences, and this is a great opportunity to educate the public in how science works or how it should work. But there's also some danger. As Dave indicated with the discussion of the different kinds of theory, there is some danger and some practice, particularly among our observational colleagues, of presenting every result as the destruction of theory that everybody believed in. So we see many press releases about the impossible planet or about how this discovery forces rewriting of all the textbooks. And this is actually, in my opinion, a very corrosive attitude, which could and should lead the public to conclude that researchers in exoplanets and scientists in general don't actually understand what they're doing, that it's a cultural construct and you can say anything you like and it just matters whether your colleagues accept it or not. And so I would urge people to take seriously Dave's more nuanced view of what you can accomplish in theory, and to try to persuade everybody who's writing press releases, whether it's press officers or your colleagues or yourself, to take a somewhat more sophisticated view of how science works than I see in a lot of the press about exoplanets in the last few years.
Sure.
Yes, I would agree with that. It is quite common within our own solar system with missions. A spacecraft arrives at a planet and something unusual is seen. And this is an opportunity to be enthusiastic about the richness of behavior, but sometimes it becomes instead an opportunity to say that the theorists don't know what they're doing.
This is somewhat related to one of Dave's comments here, that the less imaginative proposals are getting more easily funded. The more sensational press releases are getting bigger audience, so that's what you have to fight. Almok.
So Dave, you raised concerns about ignorance in understanding the disks. You said that there's no known mechanism for transfer of angular momentum. So
Well, there is a known mechanism, but
Yes.
it may not work everywhere.
Exactly.
Yeah.
So there's a work from, I think the first one was in 87, and later follow-ups that touted that proposed spiral shocks as an alternative
Yeah.
mechanism that could work even in the absence of plasma. And it's been shown that in simulations that under various conditions you can get very high values for the alpha equivalent in that mechanism. So there is a possible mechanism for accretion even in the absence of magnetic fields and ionization.
Yes, you're right. I did not mean to imply that there are no alternatives, but it is astonishing to what the extent to which one sees in the literature these days either using MRI or just saying alpha is something or other and hoping that it works.
Isn't the concern with spiral shocks that you need something to excite them?
Actually, no, it's an instability. So you start with anything and it will develop into it. Under certain conditions, I haven't tested the entire parameter space, but from the little experience I have, sometimes they can just emerge spontaneously due to an instability. It's even been derived analytically in the paper by Hank Spruitt in 87, I think.
If it's an instability, it has to start off linear, and I thought the problem was that there weren't any linear instabilities other than MRI.
That's a good question. As I said, I'm not an expert on the subject. I just know it's in simulations usually it's excited somehow, but it's a valid concern.
Just one general comment about that. I've wondered about this in connection with forming giant planets directly by instabilities in the disk, kind of work that Alan Boss has done. A common problem with those calculations, that kind of calculation, is that people start with a system that's already unstable, right? Rather than creeping up on the instability. And it really matters. Now, unfortunately, that's a difficult problem to handle. I don't know enough about the specific thing that you're describing, but that's a common problem. People don't think through how you get to the unstable state. They just do a simulation or a calculation where it's already unstable.
I agree.
As someone who's working on star formation and disk formation, like in the recent years, there's been like a change. It seems to be that there's kind of a paradigm shift towards more away from the MRI, more towards magnetic braking, which used to be considered as that you can't avoid it because you have this magnetic braking catastrophe where you can't form disks. But recently there have been more and more simulations which can include non-resistive effects or turbulence or both or whatever. You actually overcome this magnetic braking catastrophe and yet break the disk sufficiently to transport angular momentum. So in the disk community, there seems to be, because people are also aware of the MRI approach, that it is, that's kind of where the MRI comes from, like as a mechanism to transport angular momentum, and that's why all these typical disk models are used. But it seems to be that people get like a bit more away from it and a bit more, let's say, distracted or
yeah, I'm missing the word for it. So there seems to be some movement towards exactly what you mentioned in your.
Okay. Everybody's happy.
I just want to ask whether it's possible that in planetary disk could also be a starved disk or hungry disk, which I mean that the delivery time of nebulae gas is much longer than the settling time of dust grains and the core, those things. Could a rocky core or whatever core forms when the gas in the nebulae has not yet been delivered completely into the disk?
Well, in star formation and planetary system formation, you're usually in the situation where the collapse time from the interstellar medium is shorter than disk evolution times. It sounds like you're bringing this up in the context of something I said about what happens with the Galilean satellites, where that situation may not arise. But of course, that's a very different situation by virtue of being so compact, tidally constrained to being a rather small system. And so then you can have a long time scale, maybe, for delivery, but a short time scale for the actual evolution of the disk.
Yeah, that's one motivation for the question. Another motivation is from HL tau. When you look at millimeter wavelengths, you see very beautiful disk structure. But when you see optical image, the molecular cloud seems very noisy, a 3D structure. They have not yet formed a disk-like structure. So that also motivates my question, whether in planet formations it could still be a hungry disk instead of,
I suppose one possibility is that the starting point that we usually assume is more complicated. I mean, what we normally think about when we make the solar system is, a sequence like in a classic review paper by Frank Hsu, where you collapse and then you do that and you have jets and then you do that and so on. A nice simple sequence, but of course you could have a situation where you collapse and then you add a very big chunk of the mass as a separate event 1 million years later, something like that. The environment in which our solar system formed, which may not be atypical actually, we think is one where there are stars popping off, possibly a supernova. So yeah, it could be dynamically more complicated. And some of the ideas for Sedna are based on the notion that there are other stars passing by or even companions.
Also, I have a general concern, that is when you say a generality probably does not work for planet formation. But as a physicist, I think physicists more like them to work out like principles which are right for everything or for most things. So how to say, as a physicist, okay, so what would be the right direction to work in the planetary science field if generality fails?
Well, you do have universality of process, I think. That is, you can make a list of the physical processes that matter, but the context in which you apply that process can vary. So, an example of a process is what are the specific circumstances that cause differential rotation in the atmosphere of a planet, or what's the process that causes the magnetic field. So those things are universal and therefore generalizable, but the context the particular circumstances may not be. It may be that generalities will work. I'm suggesting that there's a possibility that it won't, and that we are in a field that's more like biology. In biology, you have underlying general principles, but as I mentioned, when it comes to making a specific story, you have to look at the specifics to see how it played out. And so it really is different from doing theoretical physics. Theoretical physics you can do on a desert island, perhaps helped along by carrying the collected volumes of Landau and Lifshitz, which are my favorite. But you probably can't do that in biology, and we're sort of in between.
Regarding your first question, does anybody know what is the duration of the class 0 and class 1 T-Tauri stuff?
A few 10,000 years for class 0. So it's also, there's a question about like among observers and theorists about so there's a discussion there's class 0 and stage 0. So the actual observation of, so you observe class 0, but it is the physical stage might not necessarily correspond to it. So there's some discussion, but it's like really, it's like I think it's like a few 10,000 years for class 0.
Okay, so shorter maybe than the time scale of the
But class 1, yeah.
I think this should look into some detail. I think it's a valid question. Just a second.
So it's actually a following point to the one you mentioned before about the biology aspect and the messy science based on exceptions mostly. I'm failing to see how this can be very productive, because my experience in geodynamics at least is that you can always craft a story that's going to explain your observations. And from this statement, it feels hard to, if you give me new data set of planets, I can change, or some people will change the specifics of how the planetary formation occurs. And as we were saying, there's the high entropy thing, so change a bit about how it works. And there you go, I explain your new data. But is that very, I don't want to say useful, but
so the theory of evolution in biology is actually to some extent an example of a high entropy theory, because the way the theory of evolution in biology works is that you have this general framework for which there is good evidence. I'm not attacking the theory of evolution, but the way it's actually used to interpret things is through its infinite flexibility. It's not as sharp as a physical theory in terms of what is and is not permissible, because of the extraordinary richness of pathways through which biological processes can take place. So it forms an explanatory framework, and that's fine, but it doesn't lead to the sharp predictive power that one saw in the case of Einstein's work in general relativity, or Goldreich and Tremaine with rings and so forth. It's different. It's not better or worse, it's just different. And I think we have to acknowledge that at some level that's what we're doing.
Morgan?
I have a question about moons and hot Jupiters. I don't know the time scale over which a giant planet could migrate inward, but say it started with a bunch of moons, unless that's too premature. If it gets pushed inward for some reason, can it bring its moons? Will it leave a trail of moons and stable points? Will it drop a moon in its new close-in orbit and mess up our signals? What is possible?
Well, if it's migrating inwards in type 2 migration, and the moon is well within the Hill sphere, which is true, for example, of the Galilean moons, there's no problem. They'll be perfectly happy. You can get rid of moons by bringing another object into the system. So for example, if you're still building planets and you've got a giant embryo that wanders by, doesn't hit, let's think about Jupiter. If you have a giant embryo that goes by, something the size of the Earth, say, or a few times the mass of the Earth, that can certainly get rid of the moons, okay? That's not migration. That's just gravitational disturbance by something entering the system.
And they could bring water from another planet.
Whatever. What is true is that many of the Kepler planets are unlikely to have moons, just simply because they're so close to the star. Because you've got to put the moon inside the Hill sphere, and the Hill sphere, well inside actually, the Hill sphere, and also because of tidal evolution. For example, if you take the Earth-Moon system is actually stable at the orbit of Venus. If you start moving it significantly further in, it's not. The Hill sphere at the Earth is 200 odd Earth radii. The Moon is at 60. Of course, it's at 60 because of tidal evolution. But there comes a point where that system is no longer stable. So a lot of the planets that have been discovered so far should not have moons anyway, because they're so close to the parent star. But once we collect more data for more distant planets, it would, in my opinion, be surprising if we found they had no moons.
I think if you take our Jupiter and you'll make it into a hot Jupiter on a 3-day orbital period, the moons will be ejected, and they will probably collide with Jupiter. So they will be swallowed by Jupiter.
So they won't go to another planet.
Probably not. I'm just thinking this up right now, but I think they will collide with Jupiter. Please.
Yeah, so this just goes back to the point that was brought up earlier and that you had mentioned, which was that if something is physically possible, then it will likely at some point exist somewhere. The analogy with
that's the history of astronomy. You look at a new wavelength and you suddenly see a whole bunch of things.
And the analogy with biology and evolution is the correspondence is kind of 1-to-1, because it's extremely unlikely that somebody will be born with 3 eyeballs, but I'm sure that there's somebody somewhere in all of human history who was born with 3 eyeballs. It's not statistically likely, but it's the probability still exists. So especially, and Yoram kind of touched on this a little bit when he was talking about the possible mechanisms for forming, say, hot Jupiters. It'll ultimately come down, I think, especially when we're talking about planet formation and mapping that back to the observed diversity of exoplanets, it'll be in discussing the statistical likelihood of certain processes to yield what we see now. And it's not going to be a simple picture, even though we like to show diagrams that go, okay, this happens in the disk, then we have a coagulation, then we have gas accretion, or this or that. But it'll be in discussing the likelihood of some of these processes to occur over others. And I think it's important. It's important, especially given now that we have a statistically meaningful sample of planets against which we can test our theory. But again, I guess the point is ultimately to caution against trying to come up with very hard and well-defined scenarios in trying to explain what we see.
I think the important point, and I've sort of said it already, is that there is a universality of process.
Oh, of course.
So when I talk about diversity, I don't mean outliers. There will also be outliers. That is really strange planets.
Yeah.
But that's not actually what I'm talking about. I'm saying that there will be diversity as part of the main population of planetary types.
There's no
just because even with a universality of process, there are many different possible outcomes depending on the timing of when the gas is present in the disk versus when it's lost, and how much stuff you've got, and what kind of stuff you've got. And it just seems to me that that's a richness that starts to look like the kind of richness that one sees in the pathways of biological evolution.
And just kind of another related point, and I think it's becoming clear now in the field, but that it may not necessarily have been clear earlier on, is that it's important to consider all the various processes together, and that includes both dynamics and things like gas accretion and stuff like that. And there's a tendency for people that work in different aspects of the field to focus just on that. But I think it's important to look at how all of those interplay, especially where the time scales for different processes are commensurate. So whether that's things like impacts or coagulation, gas dispersal, these are all things that are important that all happen on roughly relevant timescales. So it's not, in lots of cases, possible to disentangle the physics. And I think it'll also be important going down the line to consider all those things in a not watered down way as is sometimes done, you know, in population synthesis models and stuff like that.
Okay.
Just to build up on that, I think there is also another analogy which might be relevant. It's with archaeology, because we are trying to build a history of something, and I think as any history, if we want to go further back in time, it will become more and more degenerate. So if we want to use the building blocks of theoretical physics, the law of the universe we know, at some point I think if we want an exact story of what happened, it will be too difficult to build it even for one single system.
Yeah, of course, I would argue we're not actually trying to do that.
Yeah, yeah.
I mean, that's even true for our solar system. Although there are people who run models, we're not really trying to understand the specific set of steps that led to the Earth. We're trying to get a general picture of how we got the Earth, I think.
Yeah, yes, but
so it's not like we're a forensic scientist, you know, arriving at an automobile crash and trying to figure out exactly from the skid marks, you know, which particular sequence of it. It's not quite that, I hope.
Some people are this.
I know. Yes.
But but my point is that using what we know from the physics, we can also just make hypotheses. And I'm happy, maybe not to know what happened, but to know that something is not possible.
Ah.
You see what I mean?
Yes.
So
by excluding things, we get a better understanding.
yes.
So yes, if you can say certain things according to our understanding of how physics works are simply not possible, that's really important.
So I think if we keep on restricting what is possible and what's not, it's something which is interesting, even if we don't have a complete picture of what could have happened.
Yeah.
I was wondering, oh, here I am.
Yeah.
Could you comment briefly on like the redundancy of labor in the field and how an individual, or what kind of attitude an individual should assume to make significant contributions to the field that aren't just overlapping with the work other people are doing? I mean, I think that's what your whole talk was kind of about, but.
It's hard to give general advice.
Beg for collaborators.
Well, I would say that, that this is a subject where collaboration is very valuable. And that's a worthwhile comment, because theoretical physics, in many cases, is populated by people who don't function that way. Now, of course, the field we're in is not just theoretical physics. Theoretical physics is just a piece of the pie. But it does seem likely for many of the problems that we want to understand that collaboration is a very important part of making progress. So find good collaborators. I'm sorry, I'm not sure I can find a better answer.
Anyone else? Of course.
You want the last word? Oops, sorry.
Is there a gift for the person who asks most questions? Okay, that's great. Okay, yeah. So I just think of maybe an interesting practice, and that relates to those superpuffs found in TTVs. And okay, So let's say we have a superpuffs and it suffers from TTVs from which we can constrain its free eccentricity and forced eccentricity. But in Yoram's lecture, that seems the free eccentricity dominates. But we also know that tidal damping would damp the free eccentricity by a rate proportional to the planet's K2 over Q. So I guess by the existence or dominance of free eccentricity, we can get an upper limit on the planet's K2 over Q. Would that give us some information of the mass fraction of the envelope of the or atmosphere of the superpuffs? Or in other words, I would expecting if the eccentricity is dominated by free eccentricity, that means the K2 over Q must be very small. And that means although its radius is large, but the mass in the atmosphere, in the large atmosphere, is very little. So, so although that large thing might suffer a lot of tidal budgets and tidal interaction, but because its mass is so little, it cannot do much to damp the eccentricity. So I guess it might be an interesting practice to do to constrain the mass fraction of those superpuffs, but which make.
So if the planet that you're looking at is a rocky body and has an atmosphere that is hydrogen and helium, then actually the radius is a fairly well-defined quantity. That is, you can convert the measured radius and mass into a statement about the fraction of mass in the atmosphere. There is an ambiguity if you thought that it was an icy body, if you thought it was rock plus ice plus gas. So that's the case where it would certainly be of interest to have additional information, which I would say you might actually get from the atmosphere. But I'm not sure exactly how to do it. Certainly getting K2 would be nice.
You should also remember that we know from the hot Jupiter what is the optical period for which you have eccentricity damping. It's roughly 7, 5, 10 days, right? And most of the Earths are further away from that. Plus, they have a lower mass. And the time scale is going inversely with the mass.
Yeah, so that's why I say you can get upper limit.
Thank you. Yeah, I don't know if it would be a useful one.
Yeah.
Okay, you deserve a hug. You'll get it. And, pizzas have just arrived, and the beers are already there. So all you need to do is just go down the stairs. And I hope to see you all in Israel sometime soon. Goodbye.